Hello. Today we're going to learn about the extreme values of multivariate functions. We will be starting with 14.7 and discussing first the local minimums and local maximums. So I've got this great picture right here. It shows a mountain range. And in that mountain range, we can see valleys and we can see hills. And those are going to be the low points and the high points in a 3D world. So if you recall, in 2D, when we're working with Extrema, for example, if we had a function on an xy axis that looked something like this, then down here at the bottom, we would call this a local min because it's the lowest point in a small neighborhood. And then we would call this point over here a local max. And probably this one over here would also be a local max. And the way that we found these extrema in 2D was we would find the first derivative, set it equal to 0, and then solve. And so it's going to be similar to that here, except that we're working with multivariable functions. So derivatives are a little bit more complicated, which means finding our extreme values will be a bit more complicated. So let's see. We do also have saddle points. I don't know if you recall from 2D. So in 2D, a saddle point would be, for example, something like this. This is an x cubed function, and the point right here at the origin, that's a saddle point because it is neither the local max nor the local min. But it is something. It's something interesting. To one side, values are bigger than it, and to the other side, values are smaller than it. So it is special with that regard. And that means it is a saddle point. For us now in 3D, we're going to be dealing with something that has a hyperbolic paraboloid shape. So like this little picture right here, what it shows is that if we were to approach, this place right here in the middle of the picture, if we were to approach from, where I'm sitting, we would have to go up to get to that point. But if we were to approach, say, from the top of the hill to that point, we would be going down. So from one direction, it's a maximum. From another direction, it's a minimum. That means it's a saddle point. So that kind of gives you a picture of what the extrema would look like in 3D. Now, we're going to have processes for solving for our extrema. A few things that we need to be very careful of are that local extrema, mins and maxes, can only be found on the interior of a domain. So where that aligns with is in 2D, local extrema could not exist at the endpoints. And so for us, that means they cannot exist on the boundaries of a domain. They have to be in the interior. And the reason for that is because for a local extrema to exist, there must be a neighborhood of values all the way around it that are either fully less than it or more than it, depending on whether we're looking at a min or a max. Let's see, our extrema will exist wherever we can find horizontal tangent lines. But since we're working with multivariate functions, that means all horizontal tangent lines must have a slope of 0. And for us, that's going to mean that we're going to have to look at all first partial derivatives and when they're equal to 0. So let's go over this list of how to find local extrema. It's definitely a step-by-step process. Your job will be to remember this process. Practicing it enough times and writing out what your steps are each time is going to go a long ways towards helping you be prepared to do that. So the first step, we're going to have a function z equals f of xy. So our function will have x's and y's in it. And what we're going to do is find the first partial derivatives. So f sub x and f sub y. Then in step 2, we'll have to set those equal to 0, and we need to solve these simultaneously. So what that means is that we're not trying to find where one of them is equal to 0 at a time. We need them both equal to 0 at the same time. And that's going to look different for different functions that we work with. But ultimately, you can't just take one y value and say, oh, okay, that's where my critical point is. You have to also find an x value, and the x and y value together must make both first partials equal 0. We can also look to find where the first partial derivatives do not exist simultaneously. Okay, so I guess I kind of talked about that in step 3, solving the resulting system to find what values of x and y will make both partial derivatives equal 0 simultaneously. Once we do that, we will have our critical points. We're going to find one or more, or maybe even none, critical points when we go through this process. And what we need to do is make sure that those points that we find are definitely in the interior of our domain and that they're not on the border. So for our class and the problems in our textbook, with the local extrema problems, they don't usually give us a border, so we're pretty safe there. However, this method will get repeated when we're looking for absolute extrema, and that's where it's going to become important that we make sure that those critical points we find are in the interior. For each of the critical points that we find, we'll call them a point A, B, we're going to have to use a multivariate second derivative test. So this is kind of similar to what we did in Calculus 1 with the second derivative. With the second derivative, we are actually going to be finding all the second derivatives, so f sub xx, f sub yy, f sub yx, f sub xy. And then we're going to build our second derivative test. Now, in Calc 1, the second derivative test was about finding the second derivative and setting it, or in evaluating our second derivative at our critical points and seeing what sign we get. That gave us information about whether we are dealing with a max or a min. The second derivative test here is a bit more complicated. So it's going to be this big D of xy, that means it's a function, and it's going to be equal to the product of the f sub xx and f sub yy minus the square of f sub xy. Now in here, what this actually is f sub xy times f sub yx, but those two are typically equal. And so we can just write it as one of them, f sub yx all squared, or f sub xy all squared. I typically just go ahead and calculate both of them and then substitute them in here. Now, we have our second derivative test. That'll be some function. Then we're going to evaluate big D, the second derivative test, at each critical point. And the values that we get, we're not really worried about what the numbers are. We're worried about the signs. So if our big D evaluated at the critical point is greater than 0, and the second derivative with respect to x is positive, so we have big D positive and f sub xx positive, then what that means is f of AB is a local minimum. On the flip side, if we again have big D greater than 0, but f sub xx is negative, that's going to mean that our critical point is a local maximum. And one more here, if our big D is negative, that's all we need to know. If it's negative, then our point is a saddle point of our function. The last one says if big D is equal to 0, we know nothing. We can't make any conclusions. It gives us no information. The point could be a max, could be a min, could be a saddle point. We don't know. Okay, we don't have enough information for that particular point. Okay, sometimes people can remember the second derivative test by doing the following. So to remember the formula for D, you can write it as a determinant. You don't have to do this either, but you can. Big D equals, and then we'll have a determinant. with f sub xx and f sub xy in the first row, and then f sub yx and f sub yy in the second row. And then we calculate that determinant, like a cross product. So we'll get f sub xx times f sub yy minus f sub yx times f sub xy. And that's going to be our big D function. Hang on. Okay. All right, so we have a lot of steps to go through in order to calculate to calculate our local extrema. So let's get started on an example to see how this is done. All right, first example, we are asked to find the local maximum and minimum values and the saddle points of the function. Now keep in mind, you may or may not have mins, maxes, and saddle points, but we still have to go through the process and figure that out. We will first find critical points, then we will calculate our second derivative test, then we will evaluate our critical points in the second derivative test, then we'll be able to classify what we have. Okay, so first, we are going to solve f sub x equals 0 and f sub y equals 0 simultaneously. Okay, so that means I have to calculate f sub x. F sub x will be equal to y minus 2 minus 2x. I'm going to set that equal to 0. And f sub y will be equal to x minus 2 minus 2y, and that will also be equal to 0. Okay, I could solve for y in the first equation and substitute it into the second equation. So in the first equation, y is equal to 2x plus 2, and I'm going to substitute it into f sub y. That means I'll get x minus 2 times the quantity of 2x plus 2 is equal to 0. So x minus 2 minus 4x minus 4 is equal to 0. Moving stuff around and combining like terms, I get negative 3x is 6, which means that x is equal to negative 2. Okay, now I'm supposed to take that and substitute it back into what I have for y. And that means y will equal 2 times negative 2 plus 2, which is equal to negative 4 plus 2 is negative 2. Okay, so I get a critical point of negative 2, negative 2. Okay. One thing I can find right here is the function value at the critical point. So f of negative 2 is going to equal negative 2 times negative 2 minus 2 times negative 2 minus 2 times negative 2 minus negative 2 squared is 4. So minus 4 minus 4. This is going to give me 4 plus 4 plus 4 plus or minus 8 for a grand total of 4. Okay, this is my first step. I solved my first partial derivative set equal to 0 simultaneously. I made it a system of equations, and I used a method of substitution and found a critical point of negative 2, negative 2. My next step is to calculate the second derivative test. I want big D, which is equal to f sub xx, f sub yy, minus f sub xy times f sub yx. I need to know the sign of that. And then I also just need to know what the sign of f sub x is. All right, so I'm going to calculate those. Notice that up above we already have the first partial, so I'm starting from those. And I want to calculate f sub xx. So I'm taking the derivative with respect to x of the first partial. That's going to give me negative 2. Okay, so right away, I know now that my second partial with respect to x is negative. That's giving me some information. Now I want f sub xy, and going back to my first partial with respect to x, when I take that derivative with respect to y, I get 1. Now I'm going to look at f sub yy. Going to my f sub y The derivative of that with respect to y is negative 2. And then f sub yx is going to give me 1. Okay, so using all of this, I can go ahead and put together big D of xy is equal to f sub xx, which is negative 2, times f sub yy, which is negative 2, minus 1 times 1. This gives me 4 minus 3. No, it gives me 4 minus 1, which is 3. And that is a positive number. And f sub xx of xy was equal to negative 2, which is a negative number. Now, notice that big D was positive and f sub xx is negative for any xy values, because we didn't get any x's or y's when we calculated those derivatives. We just got numbers, and that's just saying like those values, big D and f sub xx, they're always positive and negative respectively for any xy we plug in. So if we go back real quick, let's look big D positive and f sub xx negative. We go back up. That looks like case 2 right here. So what that means is my critical point is corresponding with a local maximum. Okay. So at this point, we can go to our third step and we classify the critical point or critical points. We will have more at times. So if we look at big D of negative 2, it's equal to 3, which is positive, and f sub xx of negative 2 is equal to negative 2, which is negative. So f of negative 2, which we saw up above was equal to 4, is a local minimum. Is that what I meant? Negative frown, no, that's maximum, sorry, is a local maximum. So I should share with you my little trick for remembering this. It's kind of silly, but it's always worked for me. I know the big D has to be positive. That's true for the mins or the maxes. The one that I stumble on is the f sub xx. Like, what does it mean if it's positive? Well, if it's positive, positive things make me happy, which gives me a big smile. And a smile has a minimum value. So if f sub xx is positive, I have a local minimum. But if f sub xx is negative, negative things make me unhappy, which makes me frown, and a frown has a maximum. So that means that when f sub xx is negative, I have a local maximum. I know it's silly, but maybe that'll help you remember. Okay, so I have a local maximum. There is no local min or saddle points. Okay, so we're done with this problem. We found a critical point in step 1. We calculated the second derivative in step 2. We classified our critical points based on the second derivative test in step 3 and found we have one local max and nothing else. Let's try another one. In the second one, we're same thing, trying to find our extrema. F of xy is x squared plus y to the fourth plus 2xy. We're going to go through the exact same steps. Okay, so first we are going to solve f sub x equals 0 and f sub y equals 0 simultaneously. So we first find those. F sub x is going to equal 2x plus 2y, and that's set equal to 0. And f sub y is going to equal 4y cubed plus 2x, and we'll set that equal to 0. Now, it looks like in each one of these I could solve for x, and then, or I could solve for x in one of them and then make a substitution. So I'll do that. I'm going to solve for x in the first one. This means x is equal to minus y, and I'm going to substitute it into f sub y. So I get 4y cubed plus 2 times negative y is equal to 0. Now it looks like I could factor this and solve, so I'll factor out a 2y. That leaves behind a 2y squared minus 1. That's equal to 0. So I get y is equal to 0. Y squared is equal to 1/2, which means y is equal to plus and minus. Don't leave those minuses out. 1 over the square root of 2. Okay, now, so those are 3 different y values I got, and they all need a corresponding x value. So if y equals 0, then x equals 0, and the critical point is 0, 0. Okay, and we know f of 0, 0 will be, it looks like it would give us a big fat 0. Okay, if y equals a positive 1 over square root 2, then x equals a negative 1 over square root of 2 because x is equal to negative y. And the critical point is negative 1 over square root of 2 with positive 1 over square root of 2. And the function value of negative 1 over square root 2 and positive 1 over square root 2 will be, looks like x squared would give me a half, y to the fourth would give me plus a quarter, and then plus 2 times, it looks like a negative half when I multiply those two together. Okay, and if I get a common denominator of a 4, this is going to be 2 plus 1 minus 4 all over 4. Okay, so it's going to be a negative 1 over 4. Is that what I got before? Doing math while being recorded is difficult. Let me see. We got a negative symbol. Okay, 1/2 and 1/4 minus 1. So we've got a negative half plus a quarter is a negative quarter. Yeah, okay. Not trusting myself. Okay, last one is if y is equal to a negative 1 over square root of 2, then x is equal to a positive 1 over square root of 2. And the critical point is positive 1 over square root 2 and negative 1 over square root 2. And the function value evaluated at 1 over square root 2 and negative 1 over square root 2 is going to give us, again, we're going to square everything. So we'll get a half and then a fourth and then plus 2 times a negative 1/2. We're getting a negative 1/4 again. Okay. All right. So at this point, we have our critical points. We have 3 of them. And I already went ahead and found the function values because we're often asked for what is the local maximum value. That's going to be your z value. Okay. All right. Second step is to calculate the second derivative test. And that's the big D of xy equals f sub xx times f sub yy minus f sub xy times f sub yx. And we also need to see what f sub xx is and what its sign is. All right, I'm basing this all off of the first derivatives that I already found up above. F sub x was 2x plus 2y, so f sub xx is 2, and f sub xy is also 2. That wasn't bad. All right, now f sub y, starting with the first derivative with respect to y, if I take that derivative with respect to y again, I get 12y squared, and f sub yx is 2. Okay. So now I'm going to calculate big D. D of xy is f sub xx times f sub yy gives me 24y squared minus 2 times 2 is 4. Okay, so that has a variable in it. I don't know if things are going to be positive or negative. Pretty sure they'll be positive for most y values, but for some, no. All right, so, and I have my f sub x, it's equal to 2, which is always positive. Okay, well, if my second partial with respect to x is always positive, positive makes me happy. That means I should probably be finding some local mins. Depending on the sign of D, if D is positive, I'll have local mins. If D is negative, I'll have saddle points. All right, so let's go ahead and evaluate. So we're going to evaluate big D at the CPs and classify the extrema. Okay, so first critical point, let's go up here and just look at this. We have a critical point of 0, 0. We have a critical point of minus 1 over root 2 with 1 over root 2. And we have a critical point with positive 1 over root 2 with negative 1 over root 2. So big D of 0, 0, that's the first one, is going to be 0 minus 4, which is negative. Okay, and we don't even care about the sign of f sub xx. If big D is negative, this means that f of 0, 0 equals 0 is a saddle point. Okay, now let's look at big D of negative 1 over root 2 with positive 1 over root 2. Plug that in. We're only concerned about the y value and then squaring it. Squaring a 1 over root 2 gives me a half. So I get 24 times a half minus 4. It's going to be 12 minus 4, which is 8. That's positive. And f sub x equal to 2 is positive, which means that f of negative 1 over root 2 with positive 1 over root 2 is a local minimum. Okay, and then we can do the last one. Big D of positive 1 over root 2 with negative 1 over root 2 is going to again be 24 times the half minus 4, which is 8. And again, that's positive. And again, f sub xx is equal to 2, and that's positive, which means, oh, I forgot to include the value. F of negative 1 over root 2 with 1 over root 2 is equal to a negative 1/4. So this also means the same over here. F of positive 1 over root 2 with negative 1 over root 2 will also result in a negative 1/4. And this is a local minimum. Okay, so that's one more problem. Again, same steps we followed through with. We solved the first partial set equal to 0 simultaneously, and then we found our critical points based on those solutions. We calculated the second derivative test so that we had something to test our points in, and then we evaluated our critical points in the second derivative test so that we could classify our extrema. We have a local minimum, we have a saddle point, and there is no local max. Okay, so that's how we work through the local extrema. I'm going to stop right here after local extrema. I'll make another video for the absolute extrema, which is just the second half of 14.7. Please reach out if you have any questions.